Alright, now, it says, how long is it going to take for it to double when you have a growth rate of 1.2? So if you take x and say it's going to be 1 plus 0.072 to the t power, this is your original population. You want it to double. So you want it to be equal to 2x. So if you divide this by x, we're going to get 1.072 to the t power is equal to 2. Now, at this point, you can do a couple different things. You can plug in, you can have this in your calculator and plug in 4, 1, 28, and 10 and see which one is going to get you closer to the number 2 than anything else. But there's a way that you can actually solve for t. Now, you take, what you have to do, first off, is you have to have the equation where you just have something to the power of t is equal to another number. You can't have other variables in there or else it's not going to work. So you have to simplify it down to where it's just, we want a to the x is equal to b. That's what we want it to be. Now, the thing that you do is we're going to use something called a logarithm. And so we're going to use, let me move this over here. We're going to use this, the natural log, ln. It's on your calculator. And I'm going to say, I'm going to take the natural log of 1.072 to the t power is equal to the natural log of 2. Now, does this violate any math rule that we've learned so far in the past? Can we do the same thing to both sides of an equation? That's a rule that we have. We can add something to both sides. We could subtract, multiply, divide, raise to a power. Now we have this thing called a natural log, which we haven't really worked with yet. We're going to work with after the semester break. We're going to work with logarithms and we're going to work with natural logs. But this, to kind of let you know how you can work with that, I wanted you to see if you can fight through the answer first. And if you got to this point, like I said, you could just plug in the different answers and go from there. But here, this is the actual math behind it. If you have this situation where you take the natural log of something to a power, you can actually bring this out front and say it's going to be t times the natural log of 1.072 is equal to the natural log of 2. So using a natural log to solve for a variable when the variable is an exponent is something that is extremely powerful and used a ton. So divide both sides by the natural log of 1.72. So t is equal to the natural log of 2 over the natural log of 1.072. Now you dump it into the calculator. So we have our calculator, and I dumped it in the calculator and I got t is going to be 9.969. What's that really close, or and then another 6. What's that really close to of our answer choices? 10. So t is going to be about 10. So if we plugged in a 10, that's what's going to happen. The thing is, you don't need to know the original population if you know it's going to double. Because once you divide out that x, the original value, then you're just working with growth factors. what your original growth factor is and where you want it to end up being. So this natural log, this way of using a natural log to solve this type of a problem is one of those big things that you use in math, and especially when you're doing exponential growth. And I'll be honest, one of the things that we haven't done is talk about natural logs and logarithms before we talked about exponential growth and decay. But for right now, I just want you to press your I believe buttons and say, all right, well, I can use the natural log to solve and to get an exponent out of the power position and back into a position that we can solve for. Otherwise, you can just do brunt force math right here, where you just plug in values until you get the right answer. Now, just really quickly, since I'm going to have this, I'm videotaping it right now. It's going to be up on the web before you guys even get out of here today. If you have a to the x equals b and you want to solve for x, first thing you do, take the natural log of both sides. So you're going to take the natural log of a to the x is equal to b. And right now, you don't need to know what the natural log is. We will talk about what the natural log is eventually. But right now, you don't need to know it. And Nathan doesn't really need to know it at all because he's sleeping. Now, by taking the natural log, one of the rules, logarithms and natural logs have their own set of rules. One of them, basically what we can start doing is we can start expanding and contracting them. And by expanding them, what we're doing is we're actually taking advantage of multiplication principles. That guy can come out front. X times the natural log of A is equal to the natural log, I forgot to take the natural log of B, natural log of B. So X is equal to, if I divide by that, it's the natural log of B over the natural log of A. So if you take the natural log of both sides, move x from the power to the first factor, and then 3, solve for x, you'll be able to solve problems like that. And that takes away from having to actually know the original value of your population because it'll divide itself out. Your starting values divide themselves out. Other things happen where you're just left with growth. You're dealing with growth factors. You're dealing with whatever factor you're going to end up with, things of that nature. So use your natural log when you can, if you need to. They're not all going to be like that, but a lot of times that's going to be a really nice thing if you're solving for the amount of time it takes for something to happen. If you're solving for populations, then you're going to have a time of some kind in there already. But if you're solving for the time that something takes to grow or decay, you're going to want to use a natural log to get at that x value, or get at the t value, which is your time value. So keep that in mind. Yep. This is good math. This is... Yeah, the natural log is above the e to the x, which is on the line with 1, 2, and 3. It's the far left of that.